Okay, so thanks the organizers, especially Vahid, for this invitation here. Um, okay, so I'm talking about what we do at NERSC a little bit, and so we at NERSC, we are specialized about the single model training, so we don't do hyperparameter optimization. And how do we do this at extreme scales? Extreme scales means like thousands of nodes, so with really large batch sizes. So it's more about like the scalability challenges, but I will also talk a little bit about like the physics in the first few slides. So we are the production facility for like DOE research, so we cannot cherry pick our users, such as, for example, Oak Ridge can. We have to take all of them. So we have about 7,000 users with like 700 codes in general, and they basically spread across all the different like DOE areas of science. Just like for example, bioenergy, material science, chemistry, and high energy physics, astrophysics, and also nuclear physics, plasma physics. And naturally, we have a lot of users who want to try deep learning because we also have a strong correlation with experiments. It's just a selection, especially here, Atlas, Alice is to mention, and for example, also Diabay, the neutrino experiment. So, and these users mostly are interested in deep learning, and this is why they come to us if they already have an NERSC allocation, for example. So the main HPC system now at NERSC is Cori. It's listed on rank 10 in the top 500. So this is the last, like the list updated last week at IC. It's a 9,700 nodes of Intel Xeon-Phi 7250. So I don't want to go into details here, but in general, you have this high-speed memory, which is very useful for certain applications. For deep learning, it's more like the AVX 512 and the 68 cores, and you have the high-speed interconnect of diameter 5. So it means for communicate from every node to every other, it's like 5 hops at max. So I'll talk about this system mostly. I have some results on Sustained. So we also try to do some comparison GPU systems, especially in terms of scalability. But so this is the system I'm mainly talking about. So I think I do not need to motivate this here, but just go through it again. So why do we want this? I mean, when we, for example, talk to folks at universities or like smaller labs, when they design a neural network model, they have a GPU in mind. So they say, okay, we will design a neural network which fits on the GPU. So, and then we tell them, don't constrain yourself with this. So if you have a model which does the job better, or which you think can do the job better than this, but it's too big to fit, for example, on a single GPU, then let's just come up with something else, right? So think big, right? And still, you want to do rapid prototyping, right? You don't want to train your model for 2 weeks just to see that it doesn't work very well. So you basically want to start training your model in the morning, and then at a coffee break, you have first results, and then you can iterate over the parameters and so on. Or like doing this in an automated fashion. In general, you want to have a rapid turnaround. So after like 2-3 weeks of work, you might have something which works very well. And also the volume of scientific data sets can be large. So the question is how much data you really need. I think this is also, in general, I think one of the DOE main goals to identify basically the intrinsic complexity of the data. But in general, you don't know, and you might have like a petabyte of data, and you don't know. You cannot train that on a single node. And also the data sets can be very complex, high dimensional. For example, you can have hyperspectral imaging with like thousands of channels and things like this, right? Or they can be highly unstructured, like graphs, things like that. And as I said, your machine learning models might become bigger. In that case, you want to explore model parallelism. So it was really explained. So everybody's maybe assumed that everybody knows how that works. I just repeat this because I don't know if everybody's familiar with how data parallel training works. So in general, this applies to all stochastic gradient descent type algorithms. So basically the training algorithms which are used nowadays. So during the forward propagation, this is node local. So every node computes the forward pass and the loss. And in the back propagation part, you compute the gradients per node. And you issue basically an all reduce over all the different nodes involved in the process. So this is the synchronous training. The nice thing is you can hide this all reduce. So the node doesn't need to wait for this all reduce to finish. It can go on to the layer n-1 and so on. and compute the gradients, and only at the end you have to basically wait for the all reducers to finish. So that means you can nicely hide communication behind computation, which means that, so which is one reason why why deep learning training scales so well in terms of computational efficiency. So there are different modes. We explored all of them basically. This is why I will mention it shortly. So the synchronous one is this, the one I explained before. So you have all the nodes and you have an all reduced step. So everybody is waiting for everybody. The good thing is you have a stable convergence, so you know exactly what your batch size is, because it's just the number of nodes times the local batch size. The thing is that the scaling can not be optimal or might not be optimal. So if you have a slow node in your system, or broken network connection whatsoever, it might be that everybody waits for just one guy. And the other problem is that your global batch size grows the number of nodes, and if you make it too large, you lose a lot of noise in your batches, which means your stochastic gradient descent you will sacrifice performance on this. The fully asynchronous way, okay, you have all the nodes communicate through some parameter server. I think this is how Google implemented it in TensorFlow by default. This is very resilient in the sense that if one node drops out, this node drops out. That's it. So it will still continue to train because nobody waits for anybody. Just the parameter server needs to be reachable all the time, and then you're fine. But of course, when you have something like this, what will happen? A worker communicates the gradient to parameter server. It will integrate them and ship back the model. The parameter server keeps track of the model at all times. The issue is that if, for example, this node then comes and ships off its gradients to the parameter server, the model is already outdated. So when you have your optimization manifold, the gradients you compute are basically not the gradients which belong to the point, so at that point in space. So that means if you have a large number of workers, your gradient will be so much outdated that you can either discard them, but then the work was basically done for nothing, or if you integrate them, you basically have the wrong approximation. And of course, technically, the parameter server can be a bottleneck as well. For the hybrid one, this is we used in the SC, in our large-scale computation SC 17 submission last year. What you can do here, you can mix the best, you can mix these approaches to get the best of both, meaning that you have basically compute groups which do fully synchronous updates, and these groups talk to each other using some asynchronous, like parameter server. So the pros here are that in general, you can have a straggler in one group, so the whole group will be slowed down, but not everybody else, so this is good. And also you can control the stochastic convergence better, right? You can make, if you have problems with convergence here, because of asynchronicity, you can make the groups bigger. If you have, if your batch size is too big and you want more asynchronicity, you can make the groups smaller and have more of them. In the cons, of course, you have another parameter to tweak, which is the group size. And this is correlated with the learning rate and all the other parameters, so this is not easy to do. What we did here in that case, we basically did, for the parameter servers, we employed one per layer technically. So you can do multiple per layer, but this basically does not put a lot of pressure on a single parameter server. So the deep learning models, so we trained with this. So this is the one we trained with this in Caffe. So this was for last year. Is this binary classifier called HepCNN. It's a very vanilla binary classifier, because this was one of our first attempts to do this at massive scale, and it basically just picks up from from a detector with. So this detector is basically based on the Atlas detector, but the shapes doesn't exist. So the image size is 224 by 224. It's a bit more high resolution than Atlas actually has. So the calorimeter. And so it was trained to tell apart RPV, so R-particle SUSY events from standard model events. Then we have a newer application. So I will come later, but I will explain this later. But so I will show it here now to introduce both models we used in general, that you are not surprised when I show scaling plots. So CosmoGAN is a generative adversarial network, and it should generate cosmological mass maps. It's just 2D images of dark matter distributions in the universe. Okay, so this is an example. This is coming from the real data set, from the real simulation, which is also very costly. And this is the generated. So the simulation is basically an n-body simulation with some ray tracing and these kind of things. It's quite expensive. So come to the SC17 submission. So this was one of the really large scale trainings of a single model. So we had two architectures. One achieved 15 petaflops. The HPC I was presenting here in that at least 12 at peak, and I think the sustained performance was not much worse, what 11.4 or something like that. And this was really a single model on Cori, up to 9,600 of the nodes, with this hybrid synchronous training approach. And we pushed Intel hard to basically get their stuff together and optimize these frameworks, basically implement a lot of these things like convolution layers for different like filter sizes and number of filters in MKLML, which has now been rebranded or basically factored out into something else called MKLDNN. But some of the technology which was developed during that time basically went into MKLDNN. And also Intel MLSL, which is machine learning scaling library, which is technically for some frameworks a drop-in replacement for MPI, which supports some kind of background it's a more explicit handling of background communication, let's say. So you can offload like messages to this MLSL server, which runs in the background, and it can do the communication for you. And the server has like some knowledge about the hardware as well. So for example, if you have very potent interconnect where you can just offload small messages to the hardware, it will do it for you. And if not, it will basically keep a thread around and spawn and progress the communication. So it's quite efficient. So this was the performance we got with this, with 2 teraflops per node on KNL. Later, Intel so basically invested a little bit more work, and they did some Vinograd optimizations to the convolution layers and got a speed up for some of them, so that in total, technically our network could have achieved like 3 teraflops in single precision. So we have not tried this one at scale, unfortunately, but I think these changes should be now in MKLDNN and available when you use TensorFlow, for example, on Intel backends. So this was the results of Caffe. As I said, this was 2017, so at that time there was not much else available you can use for scalable deep learning. So this is the weak scaling. So that means in weak scaling, that sense means we keep the local batch size constant. In this case, we used 8 per node, which was a sweet spot between like not too big, not too small. So not too big to run into issues of convergence at large scale, but not too small to lose a lot of parallelism on the node and get crappy single node performance. So I think it had like 70 somehow weak scalability. It looks bad here, but actually if you extend this to like 9,000 nodes, it goes on like this. So you lose a little bit here because this network is very jitter sensitive. So you can interfere with anything. If you see if there's a buffer in the interconnect in the NIC, if there's a buffer flush, you will see it in the timing. It's quite sensitive. We also tried to do some topological binding. So what we did, we used this hybrid approach. We had basically 9 asynchronous groups of like 600 nodes each. And technically, you can group these nodes together in cabinets. So we tried to do this. So this reduced the variance a little bit, but didn't do much besides this. Anyhow, it's a nice exercise to do. But I think part of it is also the reason for it is that we own the machine. If you don't own the machine, you might want to basically try to use some topological placement to not interfere with other jobs too much. So the total training time was 12 minutes, whereas on this data set for the same precision, it took like a couple of hours, I think like out of 20, 30 hours, something like that. Okay, so this asynchronous updating was actually helpful here. So this is the loss curve we got on 2,000 nodes. So we measured the fully synchronous case versus like these hybrid cases with different numbers of groups. And what you can see here, this dashed line is the worst case we got. So this was an early stage machine. We had a lot of like nodes which were like broken, or like the software was not very well configured. So when you get a machine, so we had this machine for like 2-3 months, right? And then you need to configure that. I think the Oak Ridge folks know that from Summit. So it didn't work very well sometimes. And what you can get in the worst case, something like this, so horribly inefficient. Whereas, to be fair, so we reran this a couple of times till we found a loss curve which looked much better in the synchronous case. So this is the blue one. So this is a more fair comparison. But technically, this one can hit you any time, and then you have something like that. And the more hybrid groups you employ, of course, up to a certain like point, the faster convergence is up to like a factor of 1.6 x. What you see here, this red, by the way, this looks a bit funny. The reason for this is that this is technically, this was run the same partition of this one. That means here you see that one group is contributing old or stale gradients all the time, and you get these spikes in the convergence history. Still better than that, but if you have more groups here, you would just basically smooth this out and won't affect much. So in the end, you get some kind of resiliency from this. So this was Caffe, this was the past. So the future is TensorFlow, you know, or like PyTorch, or like these hyperactivity frameworks. So fortunately now, TensorFlow uses these optimized backends like MKLDNN. You can still compile with MKLML, and the interesting thing is that they have not merged all the functions over. So some layers are more efficient MKLML still, but I told them they should move them over. I don't want to use it because some of the layers are just not shape compatible, and you run into a lot of problems. And there's like QDNN, of course, which is much more mature, much older also. So by default, TensorFlow supports this gRPC. I can tell you, don't use it. It's really annoying. First, it's really annoying because you technically have to talk. You have to set up like a list of all the nodes you want to talk to. And it exchanges like protobuffer messages, which is very inefficient for high-speed interconnects, and there's a lot of overhead. And you can see this from the advertisement. It can run on all the different different clients, different operating systems. So it's not something you want to use for HPC. It comes with a lot of overhead, and it even deadlocks sometimes for no reason. So fortunately, there are these relatively new players for, like, I call them scaling enablers, which are Horovod, and for us, like Horovod and the Cray DL scalability plugin. They even have a nice logo now. So unfortunately, this only works on the Cray at the moment, but they might open source it for other machines as well. So that's like in the air, but that might happen actually. So look forward to this. So how do you do this? So there's Horovod. Then Intel has a Horovod implementation with an MLSL backend, so the same thing we use for this large-scale stuff in Caffe. And there is a Horovod you can compile against nickel. So in general, like the basic Horovod is a compile against MPI, which is already much better than gRPC. And in general, like these are just wrappers for like gradient reductions. And the cool thing is, no matter which of these guys you use, the source code itself is compatible. You can just annotate your TensorFlow program. If you do it right, it might just be 3 lines of code you have to add or change. And then you can just use any of them. So nickel is very advanced, so is MLSL, because they have a lot of like background processing for communication. So like MLSL, you can spawn as many background processes as you want. Nickel does this automatically by spawning millions and billions of threads. Sometimes at the beginning, you couldn't scale out very, very much because it was a bit buggy and had some deadlocks, but I think this is now more or less settled. And it's especially optimized for fat nodes. So if you have, because you use GPU to GPU, so GPU direct basically, or like for NVLink. So if you have like nodes of like 8 or 6 GPUs in them, you should try to use nickel. The CPE, so the Cray Programming Environment Machine Learning Plugin, CPLML, it's basically similar to what Horovod does. You just annotate your TensorFlow code and you are happy. So it will just basically do this with updating. The issue is the syntax is different. So you cannot run a CPML code with Horovod, for example. It doesn't work. The cool thing is it has some sophisticated features. It has gradient pipelining, so that means you delay the gradient update by 1 step. So that means at a step n, you apply the gradients computed at step n-1. The advantage is that you can basically, you can pipeline this. You can hide even more communication, right? Because the gradients can already be communicated, and what you actually do is communicate the gradients for the next steps. You don't care about them at that point in time. And it can also do the multi-threaded comms. It uses RDMA natively. It doesn't even go through MPI. I think so. Talking to the developer, he said that it basically just talks directly to the fabrics. It has some kind of algorithmic features like cooldown for Adam. So for example, for a large batch training, this cooldown, I think it. What does it do? I think it affects the learning rate at the end of the training process, so that you can also do like you can set the transition point where you want to go from no pipelining to pipelining. Basically, if you have a network which is relatively unstable at the beginning, but you have stable training in the end, you can basically say don't do pipelining and switch it on after like 30% of my training, and then you get the benefit. So these kind of things. So I did some strong scaling studies. Strong scaling is nice because you don't need to tweak the hyperparameters. If you tweak them for like single node and you want a strong scale, you basically you can just do this without changing it. The issue is you don't want to do that because none of these frameworks is really nice, like works well beyond like 16 or say like 16 nodes or so. This is what you expect. You run out of parallelism, right? So that's the problem. However, if you have a model which is like annoyingly hard to tweak at scale in the weak scaling sense by increasing the batch size, you can still do this up to like 16 node, and you can get 16x about like performance improvement. So I don't want to go into detail here. So it looks like a CPML plugin is much worse, but actually it's not. It's like this also has a large error bar here, right? And like in the region of interest, they all perform equally okay. So for weak scaling though, so this is CosmoGAN again. This is much better. You can go up to like 2,000 workers on Cori, which is 2,000 nodes, because we have like 1 kernel per box. So here Horovod MPI breaks down a bit, but okay, honestly, so like 1,000 nodes, it's still like very good, right? So this is the plain solution. This might be due to how Horovod works. So Horovod has one deficiency. It has basically a tree-based communication. So not tree-based, basically one-to-all communication handshake protocol. So what it does, so the TensorFlow graph or the TensorFlow execution is highly asynchronous, right? You technically don't know what op will be executed at any given point in time, because it has a data flow graph and it just matches the dependencies and executes elements. So that means even though you think of a neural network being basically transversed in like top-down order, it can be that you have like branching points or whatsoever in your network, and then you don't know which parts will be updated first. So what you need to do is you basically need to talk to the nodes and ask them, so actually what tensors are ready to reduce. So which nodes have computed, for example, what tensors, right? And then you basically, what the original Horovod does, it sends it all back to node 0. Node 0, so like a list of tensors, like I think identified by the TensorFlow names. Then node 0 goes along and sees, oh yeah, wait, so this is ready on all the nodes, and signals the rest of the nodes that, so please reduce this tensor. And this is somehow circumvented here, mitigated. They do like some tree-based reduction algorithm, which is much better because on the way, like down the tree, like up the tree, you basically reduce the communication. And in the end, the root node won't have much to do. So this is a Cori pristine on the right. Yeah, so here, I don't know what's going on here. So you had a little bit better scaling for your network with this. So we're currently investigating. So we tried different numbers of background threads and different numbers of optimizers. So we run 2 different optimizers, and we employ 1 team per optimizer. So Peter said that this is actually not maybe the most optimal choice. So Peter Menderger is the developer of this. So we are currently investigating this here. So don't just take this with a grain of salt. But what you can see is like the variance, so the performance variance is much smaller than for Horovod. Here's also like the nickel part. I only could scale out to like 60 nodes, I think. But in the last couple of months, we optimized this, and it should be so together with NVIDIA, and it should be easy to do to go to like hundreds of workers now. So the issue was you encounter some deadlock when you go to like a certain because of some race condition. When you so like hitting this race condition became much more probable if you go to more nodes, and this was recently fixed. I think you can last updates you could go to 128, but I think you can now go to 512 or more even. Good. So this is the HPC, and just to compare to the Caffe case. So this is also why I showed you the Caffe case. The Caffe case had basically the MPI really implemented in the most so in the most like straightforward way, because you know how you traverse the network. You can basically issue it in sequence. whereas here this Horovod has this additional overhead, for example, but you see that actually the scaling is almost the same. So you have again this problem here, like the scaling like it takes a dive a little bit around like 256 nodes, but after that it's basically straight. So it's very similar. And here the issue is, so why this is much better on Pistain than on Cori? Probably because we are very jitter and latency sensitive, and here we have to deploy the CAN-L cores, which are otherwise used for computing. We have to deploy them for doing communication. Whereas here we have strong GPUs, and we have then strong Xeon processors. We can drive the communication in the background, whereas the GPU can do just what it's good at, it's computing. So in general, so this looks very consistent, what we found, and the performance is just like, that's just good. So what about the time to solution? So I want to mention, so when we did this last year, at 2017, we did not have like this new, this large batch size optimized solvers like LARC or LARS, so this layer-wise adaptive rate control or learning rate scaling available. So, and what I did here just for fun, so assume you don't want to implement these things because you have to change more code and you want to do that. Just use plain Atom, local batch of 128, just scale it up. And then, so I'm, and then just see what your convergence rate is. And so I draw the line at 0.1 because this fitted nicely on the on the plot within the given like time I gave the network to converge. So I'm sorry for the steps here. I did some epoch averaging and reset the loss after every epoch. So I did not take this out. I'm sorry about this. So I smoothed it a bit. But in general, what you can see is the efficiency. So even with this really bad algorithms, is still like 75% for like 32 workers about. So measured for the 8 worker case. So the 1 worker case doesn't even like reach that loss within this time. So that means, so which is good for our users. So we can tell them, just take your network, annotate it a little bit with Horovod or whatever, Cray CPE, and you can scale it out to like a certain number of nodes. You will still already see a benefit. And if you then want to go further, you should basically change your solver, and then you have to also do some hyperparameter tweaking. So we haven't done this at all here. This is just the same hyperparameter set and just scale it. Yes, sorry. So last thing. So GANs at scale. So we heard from previous speakers, they're very nice results. So I was not very successful with going beyond like, what was it, 16 summit nodes in getting this thing to converge. So, but we have a different network though. So this is about basically about CosmoGAN. So what happens? So what the issue with GANs in general is that the training is fragile. So maybe you notice when you download the GAN, like the Goodfellas DC GAN, for example, and just apply to any data, maybe just match the layer sizes to process this data. But in general, it works out of the box very well, surprisingly well. So when you try to tweak these parameters, it might fall apart immediately. So that's the experience we made. If you have a constrained GAN, it's usually more stable, but if it's unconstrained, it's pretty fragile. So the loss is also pretty meaningless. A GAN loss does not necessarily mean that your GAN works well. It can hint that it works well, but it's not necessarily true. And also you have no clear stopping condition. Especially if you train too long, you have mode collapse, right? So you can see this if you have a multimodal distribution. What you will see is that at some point when you train too long, it will just drop modes. And it cannot reproduce them anymore. So it will just, and you might not notice it if you don't do some statistical analysis on your output. Also, like large batches do not necessarily work well. So as I said, I think you're very lucky with that. But in general, it's not an easy thing. And these big batch boosters, like this gradient boosters, LARS and LARC, for example, they don't work very well because of the interplay between like between critic or like discriminator and generator. It can be that one gets the boost and the other doesn't. And that is exactly what you want to avoid, because what this means then that basically the generator will learn much faster than discriminator or vice versa. And then since this is a min-max game, one will lose the game inevitably. So that is not great. There's one suggestion by like, was it OpenAI? I think it was OpenAI, to use this OT-GAN, which uses the Earth mover distance. So basically OT means optimal transport. So they have a nice loss. Basically this mapping CXIYJ, which is just so for the so this is just the cosine distance between two samples. You pipe through the I'm the last one, so so this is basically a batch x. So sample xi, sample xij, and then you apply the discriminator or the critic to it, and then compute the cosine distance in this latent space. And this M is a mapping matrix which tries to do the following. It maps the distributions like between xi and yj to be as close as possible. So basically this measures the energy of, or like the entropy necessary to transform one into the other. The good thing is about this that this is made for large batches, because you need large batches to get this cross correlation correct. The bad thing is that this is a cross correlation, so you basically need to compare any batch with any other batch. You cannot do the standard batch distribution, because you technically have to have some kind of all-to-all communication between these. So what we did, we implemented that. Doesn't work very well. I will we'll talk about this right now. But in general, you can implement this. The issue is what you need to do is you need to distribute matrix multiplication. And that doesn't work very well in the frameworks you have, because most of these scaling environments in Horovod, CPE, they only provide things like OReduce. So not like what you need is like a subcoloring communicator, so MPI split if you want, and for example for row and column-wise reductions. But you can do this. You can match Horovod with MPI for pi, which is awesome. So because an MPI for pi can use everything, and the synchron algorithm can live outside the graph. You do not want to backpropagate through it. You don't need to, because by construction, the derivative with respect to m should be 0. So you can force this to be true. So unfortunately, the initial convergence studies failed. So this requires a lot of hyperparameter optimization still. So this is what you want to have, and this is what you get so far. So for this, it would be nice to have some kind of like parameter tuner, because I don't have a lot of time to do that. The great thing is the loss for this OT-GAN is meaningful. So you can first, they said they never observed mode collapse in any training, even after 50,000 epochs. They see not a single mode collapse in their data. And the loss, really, if it goes to 0, it goes to 0. So it is meaning that it learns the distribution better. So that is definitely promising. Not this plot, but in general, I think the approach. And still a little bit needs to be done. Would be nice if the frameworks will support, like, if you do not need to go through this MPI for pi, if the frameworks will offer more functionality to do more other distributed data manipulations. Yeah, so this is a single node result, and also like in up to 8 nodes we got. So this is how it should look like. Okay, so everybody, I think, agrees that deep learning is an HPC application. The awesome thing is that now, even for this high productivity frameworks, you have these enablers which allow you to easily make your code scalable or like distributed, and you can even get good results at massive scale. So like vanilla networks are usually unproblematic, GANs are more involved. Okay, can be lucky here, but in general I think this is a more complicated task. So if you can make your GAN constrained, so what you hear from everybody is that works usually better. Yes, so what I want to see is more model parallelism features or advanced MPI features in these frameworks. So so far that hasn't happened. Would be nice to have like point-to-point communication or like all-to-all operations or like subcommunicators, for example. Yeah, so this is, I want to close with that. Thank you very much. Any questions?
Thank you very much. Questions? No. I'd actually was wondering, can you disentangle the actual speed up from compute and actually data ingestion? Is there any bottleneck that of?
So so the thing is at some point. So when you violate like the basically some of the assumptions of SGD and say, okay, we stage in data locally, so like we stage a fraction of the data locally to a given node, then you can, when you scale out, you're done, because then at some point it fits into memory and then you don't have these troubles, right? On the other hand, for GPUs, we have seen that you need to take care of that. But what you can usually do is, so TensorFlow has this dataset API, and they allow you to basically launch background processes which do the staging. On KNL, it's a bit tricky because there you need the cores to do the calculations. So but also the bandwidth is better. So in that case, so you don't have the PCI bottleneck you need to go through there. Is that what you mean? Yeah. So, but what you can do, you can play around with for example, Python multiproc or something to launch like background processes and read. So we did it with HDF5. So we had a problem where we had like a lot of HDF5 files to read, and HDF5 by default does serialized access. So like even if you open multiple files through the same process, it will serialize the access under the hood, which is not great. But you can launch just background processes, different processes. Everyone will have its own copy of the HDF5 library, for example, and can read in parallel in that case. So these things you have to keep in mind. And in general, I think no file system right now is really made for these kind of things. So what I would like to see, I talked to Cray about this in general for this data ingestion thing. I would like to see another abstraction layer. So QDNN basically is decoupled from the framework. You can plug it into any framework and you get performance, right? You just need an API or something. I would like to see the same for like data feeding. I would like to see something you can run and you can talk to it from any framework. So basically provide a plugin for every framework and you can just say, give me a batch of size something from that data. Maybe you specify your data and then it gives it to you. And then under the hood, this thing can talk to different files formats, different sources, network sockets, databases, whatsoever. So that would be my dream. And I think this would be like some agnostic platform, like file system and framework agnostic kind of solution. Yeah.
I just want to, so you mentioned you don't condition the GAN on anything?
No.
You don't have auxiliary tasks?
No.
This helps.
Yeah, this I think. So we didn't know what we could condition on, but technically, so this is for this cosmological GAN, CosmoGAN. So the guy who did it is now gone. He was a postdoc, but we want to take this over. So it's basically done for a given redshift. So what we could do multiple redshifts and then condition on the redshift or something like that. So, but I think there are like more variables you can constrain on. So we try to do this next, but it's just like that's like a. That is technically what the ultimate goal was. Yeah. I mean, yeah. But the point is we don't have the simulation, we don't have the simulated data for that. So if we want to do to some other map, but no, not for Redshift. We only have one Redshift, unfortunately. Yeah.
Let's call for a question. Otherwise, let's thank Thorsten and all the speakers of the session.